So now it's recorded. All right. So today we will go into the so-called design part. Okay. Starting of the design part. Okay, where we will look into the root locus technique. Right. But before we move on, okay, just a brief review lah on our plan, right? So initially we have set this course plan, okay, at the beginning of the semester, okay, and yes, you have you can see, okay, we are at week number 7 now, okay, and we are covering the root locus technique, okay. So up to now everything is on track lah, right? So only things that we have missing out currently is we have just done our test 1, okay, and we will cover for test 2 after we finish this and the next chapter, right? So after we finish that 2 chapter, okay, by probably by week 9, right, then we can have our second test. Okay, at the same time, as you can see that the red colors one are those items that are still not yet covered or missing, right? For the assignment part, okay, so we will have a peer assessment, okay, as well as your final submission lah, at the end of that design, all right? So later on, maybe after the SAM break, then I will inform more about the peer assessment, okay, and inform more about the assignment, okay, because so far you have already started with the block diagrams, okay, did a little bit of a time response analysis, right? Then now today we will start to look into the root locus, okay, and from there we will start to come to the end of the assignment where we will try to find out what is the proper compensator, okay, in order to design for uh, our target lah, right, our block diagrams, right, so that will complete your whole assignment, okay. At the same time, there are few quizzes, okay, that are missing, okay. So these quizzes will be conducted online using Google Classroom, right? So I will again inform this probably after the SAM break, right? This one just to refresh back, okay, since we already passed through all these things, okay. After the SAM break, I will just give a simple quiz, okay, just objective questions, right? Okay, so that you just refresh back on what you have learned, okay, so that it's connect back, okay, to all these items later on, right? So also for tomorrow class, okay, since we have this event, okay, program sharing sessions, okay, so for the class tomorrow, okay, so you have to take the attendance lah, right, and attend this sharing, okay. So the attendance link already put in the Google Classroom, okay, and then tomorrow's we would not have the class but replaced with these sharing sessions, right? So these sharing sessions would be on the professional engineers, right? As you have come to graduate next year, hopefully, okay, then this is where you start to prepare, okay, what would be the criterias, okay, to become a professional engineers and how you can go through it, right? So the content would covers about the applications through road C, okay, of BEM. So probably IR Dr. Melvin will inform more about what is road C tomorrow, okay, which covers for everyone, okay, not only for academicians, okay, but since their path is through the academicians, so slightly different, okay, slightly different in terms of the requirement of the experience, but then the rest of the process is still the same, okay, same interview process and so on. So hopefully by these sharings, okay, it will benefits for all of you, okay, who after you have graduated, okay, then you see what are the missing part, okay, before you can go or sit for this professional engineers exams or interview, I would say, okay. What are the components during the interviews, how to write the technical report, experience report, and so on, okay. So it will give you an idea of what to prepare, okay. After you get your registration as a graduate members of or graduate engineers with the BM, okay, then how you can proceed further, okay, to be recognized as a professional engineer with the title of IR, right? So after you get that, okay, then you can use the title of IR, you have the stamps and so on, right? So make sure you join these sharing sessions tomorrow and take the attendance as usual. Just take it as a part of the class, right? So I hope this will benefit everyone here. Okay, great. So back to today's lectures, right? So as I say, this lecture would be on the design part, okay, on the root locus technique. Okay, so this chapter would mainly on the fundamental of what is root locus, okay, or how you can produce it, okay, or draw it, right? So this will covers the ability to draw the locus of the system in the S domain, okay. So again, we still rely on the real real axis and imaginary axis, the S plane, right? And how the root will change positions, right? So we have covered this, roughly go through on uh, the effect of the different locations of roots, okay, sorry, the roots itself, okay, or the pools itself, okay, when it shift to the left or going up or due along the radial lines, right? So how it will affect, right? So today's we will roughly go into more details, okay, on how we will draw all these things, okay, and why during the time response chapter, why we would say that you can have this roots or pulls moving up or to the left or to the diagonal. How would this possible, right? So we would slowly come into picture by drawing the root locus, okay. So as we have gone through several transfer functions, we have start with the open loop, the very straightforward, and then we come to the closed loop transfer functions, right? As you can see in this statement itself, okay, the open loop transfer function are basically quite easy, okay, where the pool will not change, okay, when you have the k value, the gain value change, okay. So meaning to say, in this particular open loop system itself, you may not able to see or you may not able to control the movement of the the poles or the roots lah, right? Okay, so just make sure you understand when I mention the pools or the roots, they are referring to the same thing, right? Okay, so the pools referring to the bottom uh, polynomials, right? And because it is in maybe in the form of uh, second order, third order, so there is a roots, right, to make it become zero. So we just interchange it lah, right? The roots and the pool. So what we trying to plot today, okay, is the roots, okay, which referring to the pool, okay, the changing of the pools itself, right? So for the open loop, very straightforward, the pools will not change, okay, by changing the k, right? But now our focus would be on the second part, okay, the closed loop transfer functions, okay. Why we would like to analyze this is because it is a little bit more difficult, and at the same time, okay, the pools actually uh, depending on the gain, the k, okay, at the denominator parts, okay. So you can see that normal transfer function for a closed loop transfer function will be in this form lah, okay, kg over 1 plus or maybe 1 minus something, right? Okay, because of the feedback transfer functions here, right? So what we will see that is that the denominator part is also depending on the k. If you change the k value, the locations of the roots or the pools will change as well. Okay, and this is where this will be beneficial for you. Okay, when you start to design or yeah, start to design for the compensator later on, right? Okay, so this is the idea of it. Okay, so now our focus would be we use these transfer functions, okay, generate transfer functions or closed loop transfer system itself with a forward transfer function with kg and the feedback with h, right? So therefore we would have the transfer function of kg over 1 plus kgh, right? Straightforward, right? So we will start to analyze the characteristic of it so that when you start to answer the questions later on, okay, you don't have to redo the mathematics. Okay, so the mathematics would be quite straightforward. Okay, so we will assume that the g is a fractions. Okay, a fraction in the form of n over d. Okay, numerators and the denominators for the transfer function g. Okay, same thing for the h. Okay, the feedback transfer function, again we have the fractions, okay, of numerators and denominators. Okay, for examples you may have this form, okay, s plus 1 over s plus 2, right? For the feedback you may have s plus 3 over s plus 4, okay, for example. So you can directly illustrate lah, easier, right? Instead of the alphabet, sometimes we may not familiar with alphabet, right? So here is how it looks like. Okay, so and when we try to put it into this transfer functions, then it may looks a bit complex. Okay, a bit complex where they consist of k, then this n itself is over here, this d itself is over here. Okay, so this would cause the so-called the zeros of these transfer functions is now consists of the zero of the g and the pools of the h transfer functions, right? So what we have here is just to form this transfer function immediately based on these two, you just have to use this lah, okay, s plus 1, okay, put it here, okay, s plus 3, sorry, s plus 4, put it here, right? So directly put in there, right? With a k as a k lah, right? Then for the denominators side, okay, therefore we have a dg dh plus k and g and h, right? So the denominators g, okay, so this part you put it in, okay, the h you the h part, okay, put it in, okay, multiply, and then same thing plus the k and so on. Okay, then simplify the bottom side. Okay, so immediately you will get this in this form, right? So once you get this form of transfer functions, okay, so you may start to realize that as we have expected, okay, the k would be affecting your roots. Okay, when you change the value of k, not only it change the gain or amplifying the response itself, but it's also changing the location of the roots or the pools. Okay, so this is where in order to obtain the performance of the system, the denominators must be a factors out, okay, must be factored out, okay, with a specific value of k. Okay, so you must like do this lah, okay, bracket it with k and so on, right? So that it's easier for you to visualize it, and from there this root locus will come to a picture lah, our pictures, okay, our purpose of today, okay, how the pools will move, okay, when the k change. Okay, see, this is our main purpose, okay, of doing this root locus. Okay, So the root locus technique can be used to analyze and design the effect of loop gain. Okay, loop gain means referring to this lah, the K itself. Okay, the loop, because this is a loop and the gain is the K, right? So effect of loop gain upon the system transient response and stability, right? So again, we always talk about the response itself, and also before we analyze anything, we should check also the stability, right? So we will also look into the stability itself. Okay, so as we recall previously, okay, we when we talk about the stability, we may say that the pulse, if it is lying on the right hand plane, okay, the positive value of real axis, therefore it is not stable. So this is how we can see the locations of the roots, okay, when it slowly shift to the right hand plane itself, okay, therefore it will turn into the unstable values, okay, when we continue to change the value of K, right? So we just take these examples, okay, of motors and cameras, okay, to detect or change the position of the camera itself. So we may have an amplifier to amplify the signal to the motor as well as the position of the camera lah. So maybe a simple uh, transfer functions over here. Okay, so this can be something similar to your assignment, right? Okay, where you also involve the motors, okay, and also the maybe you may deal with the positions or the angles or maybe the velocity of the motor itself. Okay, so it depends on what is your input and output relationship lah, that you intend to solve in your assignment. Okay, so from there, okay, would you would use a sensor, okay, to obtain, okay, the so-called positions, okay, as a feedback, so that it can be directly linked back, okay, or you may have an amplifier again, okay, to amplify the signal of the sensors and so on. Okay, so that will change your transfer functions for the so-called H, right? The H. So this part will form the G, and this part, since we don't have anything, so we let it as H equals to 1, right? So simplify it. Okay, so you would have this uh, transfer function to describe this closed loop system, right? So we further simplify K1, K2 as a K, right? So when we start to varies the value of K, okay, so we just generate solve it, okay, by changing the value of K. Therefore, I just use a simple tools, okay, I just program it in the Excel to calculate the roots or the pools for these functions lah. Okay, so we only look at the bottom side, right? Okay, the denominator. So we have the value of A equals to 1, the value of B equals to 10, okay, and the value of C is equals to K. Okay, so I varies the value of C over here, okay, the A and the B maintain, right? So I can program it in Excel to find the pools, okay, for pools 1 and pools 2 lah. You just use the equations of minus b plus minus square root of 4 b square minus 4ac divided by 2a, right? So you just apply that formula in your Excel, then you can generate your pools easily. Okay, so when I plot this out, okay, when I plot this out, then we can see that eventually, right, the pools may start over here. You can see that when the K is equals to 0, okay, the pool start from 0 and minus 10. Okay, start from 0 and minus 10. Okay, so when I slowly increase this one, then the pool change position. So eventually the pattern is it move over here and this pool move over here, right? So you can see that the changes of the pools until they start to intersect. right? So they start to intersect when this happen, when the k equals to 25, okay, then this start to happen. And when we further increase this one, then the roots or the pools now start to split again. So this one will split going up, and this one will split and go bottom, right? So this is the pattern that we obtain, okay? And we call this as a root locus, okay? Because we now we are able to see how the roots or the pools are actually moving, right? When the K is changing, right? So this is what we meant as a root locus. Okay, so you can plot it using Excel, okay? Or if you like, you can also plot it using Scilab or MATLAB, okay, which I think we will cover in the slide later on, right? Okay, so how we can construct this root locus, okay? So this chapter, our focus is only to construct the root locus and get some meaning out of it, right? That's all, okay? Before we understand further and use it as a design, as a tools to design later on, right? So for this course, we only consider a positive value of k, okay? And that root locus will represent the path of the closed loop pools, okay? When the pools are changing according to the gain, right? So we call that as a root locus. So remember, this root locus only so-called applicable to a closed loop system, okay? Open loop, the pools will not change, okay? Because no matter how you change the k, the pools remain the same, okay? Only when we apply it to a closed loop system, then changing of the gain, the k value, the location of the roots will change, okay? So when you draw it out, okay, you don't have to draw it in this way, okay? This one just to illustrate the positions of all the pools, okay? When you plot this out, okay, you just have to draw the starting point, okay, starting point, and then the meeting point, okay, and the direction. So you just draw lines on how, where it will go, okay, that's all, right? So you can see that you will mark with k equals to 0, okay, the meeting point, what is the k value, okay, and where it will goes after that, right? So this is how the root locus will looks like. And what we can see here is that based on our understanding in the time response itself, right? So whenever the roots still lying along the real axis, okay, on the left hand side, okay, therefore the system would be over them, okay, because as you can see, it's still always slipping along this flat line, right? So it's everything is over them, right? It doesn't have the ability to move up and down, right? So call lah, right? So that is how you remember the terms lah, over them. Then only at a point where they almost going to the imaginary parts, okay, they meet, and that is where we call it as critically damped, right? So you expect the system would be like going up, okay, and straight, okay, to the final value lah at this point, okay. Then after that, okay, when it start to split into the imaginary uh imaginary axis or domain itself, okay, therefore the system will now behave like the under dam, okay, it will start to oscillate, okay. So all this will represent like the time response over here, okay, it will start to oscillate, right? So the oscillations now, it depends on how far or how what is the k value lah, that you intend to put in, so that you can control the performance of your system, okay. So now this is how you can control, right? Because you already know how it would behave, okay. So if your intention is to design a system such that, okay, this system is to get what, to positions the cameras, right? Okay, so you may not want the camera like zoom in, zoom out, zoom in, zoom out, right? So this will represent like or move, move left, right, okay? So you may not want this, okay? So the best possible solutions would be you may desire this one, the fastest to reach the steady state value, okay? So immediately from this analysis, you know that when you set the K value equals to 25, it will be the fastest and the best lah, okay, for this purpose. Okay, so this is how you can start to design and relate, okay, on all these informations, okay, on the root locus. Okay, so this root locus will helps you to visualize how it will change. Right, so this is one of the examples that it move horizontal and then vertical. Right, so this is how you can form it. Right. Discussions on the root locus would be yeah, depending on your desires, specifications, okay, I would say specifications. Yeah, so it depends on what you intend to achieve. Okay, let just like what I have mentioned just now. If for a camera I would like to for it to like reach the positions without much oscillations, right? So probably I will select K equals to 25, okay? But in some cases, you may also want to consider different points, okay? Therefore, if you are considering different other values, okay, sometimes theoretically we may say that 25 is the best, but how you would set this 25 directly to your system is another question, right? So sometimes you may not able to set 25, okay? You may able to like the device itself come with maybe a resistor or whatever it is that cause the K to be higher, okay? So in that case, how you would select, okay, what would be the best one, okay? So that would affect your settling time, okay? So this is how you would see, okay? But then you can see that the settling time still remain the same since it is in the vertical form, okay? This is a characteristic of the roots going in the vertical form lah, right? But only difference is that you just refer back to the characteristic of roots moving in the vertical form, okay, how it would behave, right? So this is how you can discuss the root locus. Okay, then on the gain increase. So if we further increase this one, okay, as you may learn in the time response, okay, the damping ratio will disappear, okay, or getting smaller and smaller, okay, but the percent overshoot will start to increase, okay, when you increase the gain. Okay, so it depends on your design specification that you requires. Okay, so the damp oscillations or damp frequency of the oscillations itself, which equals to the pulse, will also increase when the gain or the K value increase, okay, which reduce the so-called the peak time and so on. So this is the typical discussions, okay, that we have discussed during the time response. Remember the first three picture that I've shown in the earlier of this chapter, right? So you just refer back to that, okay? So you may able to rediscuss all these things, okay, or get some ideas of how it will affect so that you can select a better values later on, okay? And what happened is that we also analyze to the so-called stability, right? And we say that when the pools or the roots lying on the right hand side, since the value of 0 is over here, okay, everything the real axis is still in the negative side, you will notice that the roots will only go up and down, okay, it will not move to the right hand plane anymore, right? So in this case we can always say that the system will always stable, okay, regardless of how many Ks you are going to to inject lah to the system, okay. So this is how you can see the stability, okay, of the system, okay. But later on you will start to realize that uh, sometimes it will also cross, okay, and when it will cross, okay, so all these things will come into the picture, right? So here is the properties of the root locus, okay, just some ideas of the root locus itself, okay. Previously we say that the locus is obtained by factoring the polynomial of the denominators of the transfer functions, okay. And from there, okay, after we understand the root locus, the property of it, okay, therefore we can roughly guess, okay, from the root locus, okay. So now we try to like make it faster, okay, by looking at it, okay, what are the small characters, just like the so-called steady state error, okay. We start to categorize like system type, okay. Type 1, immediately you know what is the characteristic of it, okay. So this is the purpose of we start to study the properties of the root locus, okay. Again, general closed loop transfer function as previous, okay, same diagram, right? So here is that from these particular equations now, okay, from these particular equations now, a pool's S exists when the characteristic polynomial. Okay, so where again, these characteristic polynomials refer to this bottom part. Okay, the denominator polynomials. All right, it form the characteristic of the system, right? So we call that as characteristic polynomial. Okay, so when this characteristic polynomial becomes zero, okay, then things become some problem will occurs, right? Okay, when it becomes zero. So from this, okay, therefore we start to look at this, okay. We have 1 plus kgh, meaning to say for these denominators to become zero, this kgh must be equals to -1. Okay, so we set kgh equals to -1. And this can be how in a like a polar system, when this can be -1 is when we have the one when it rotates at the 180 degree, right? Just like a circle. Right. So when it's lying on this side, okay, so 180 degree, okay, with a unit of 1, okay, so unit of 1 lying at 180 degrees, okay, so it will give you -1, okay. So if you rotate again, okay, then so this is the function of it lah. So it can be 0, again, one cycle after that, and so on, okay. So this represent the polar system of this, right? So -1 is being represented in the polar, okay, polar system itself, okay. So what we can obtain or get the meaning out of this is that in a complex number, okay, in a complex number, the result must be like if the values of the s is substituted into this particular system, therefore it will result to the system to have the pools, or sorry, the pools, sorry, the characteristic polynomial to become zero. Okay, so again, you may not see it, okay, so probably I just quickly read through these two terms, okay, then we will go into the next slide to see the so-called examples, right? So when the angles of the complex numbers is an odd multiples of 180 degree, okay, so you can see that odd number of 180 degrees is referring to again polar, okay, so it can be 1, 3, 5, and so on. So 1, 3, 5, because you can see this is an even number plus 1, so it become always odd number, right? So when this occurs, then the value of the s, okay, in the system's pool would be would be the so-called equals to 0. And when it is equals to 0, okay, when this equals to 0, meaning to say you already get the pools, right? Okay, because we would want to get the pools, okay, at the denominator. So when this condition occurs, okay, when this condition occurs, meaning to say we already found the pools of the system or the roots of the system. Okay, so this is how we can find the k value for our system, because in this particular diagram, okay, for examples, when we start to plot it out, okay, we may not want to use Excel or so on, okay, then we may have a problem like visualize what is the the values of k, okay, suitable over here. So we try to find out whether it is proper or not, or correct pools or not, by these conditions. Okay, so when kgh equals to -1 or equals to 1 at odd multiples of 180 degrees, right? So this is the conditions or the properties of the root locus. Okay, so the properties of the root locus say that if point S is a closed loop system pools, okay, we are now testing the property of it, okay, whether it is a pool or not, okay, for some gain of k value, then the S must satisfy this condition. Okay, it must be kgh equals to -1, or in an absolute form, it is equals to 1. Okay, then we rearrange this form, then the k would be equals to 1 over gh. Okay, 1 over gh. Okay, and this represent our property of the root locus. And at the same time, this must be a odd multiple of 180 degrees. Okay, the angle of the polar must be odd multiple of 180 degrees. 2k plus 1 multiplied by 180. Okay, so to test this concept, okay, as I say, okay, some examples over here. Now take this kgh probably equals to k over s multiplied by s plus 10. Okay, take this as a example lah. Okay, this examples is basically the previous examples. Okay, and we already know that when we do using Excel, we already know that when k equals to 5, then the pools would occur at this 2 point. Okay, minus 0.527 and minus 9.472. Okay, this is when we solve it like analytically lah, right? Okay, so how we can like not using Excel, okay, now whether we give a random number of pools and that random number is a valid roots, okay, how we going to test that, right? So what we do here is, okay, so we just randomly pick this k equals to 5 over here. Okay, we substitute, right? So what we do is we put the s, the roots itself, equals to maybe minus 9.47. Okay, we take this, okay, and also the k value as 5. Okay, just check a quick check of it, right? So substitute into this formula, because this formula is already easy for you to calculate, right? Instead of solving let me show you, solving this. Okay, so it may turn out difficult for you. Okay, so you just want to test, okay, whether it's correct or not lah, right? So using this method, okay, so we just use k over s plus 10. Okay, so this is our random number that we would like to test. Okay, this position we just substitute into s. Okay, S multiplied by this, use calculator, and then we use K equals to 5. Okay, just put it in. So eventually, once you calculate this one, you will get it coincidentally equals to -1. Okay, so when this is equals to -1, immediately we know that this is the pools. Okay, when K equals to 5, right? So this is how you can do a testing of whether the answer is correct or not, right? So if this is just the properties lah, okay, that you may refer back, okay, from time to time, okay. So to test if if a point S is the pool of a closed loop transfer functions, you may also draw it out, okay, draw, okay. So here you may draw the pools and zeros, okay. So what we have previously is these transfer functions, okay, exactly same transfer functions, okay. Yeah, okay, we draw it out. So for the so-called zeros, okay, and the pools itself, we just draw it like 3. So this is -3, okay, this is -4, okay, then this is -1, this is the pool, this is the 0, right? So we draw this out based on only the G, okay, based on only the G, okay, assuming this is the closed loop lah, right? So we only draw this out, okay. So once we draw using this particular transfer functions, okay, of the forward transfer functions itself, now next would be to identify the angle between the test point, okay. The test point now come into the picture, just like the previous one, we test the point, right? Okay, with the test point, and then the angle of the 0 minus the angle of the pools, okay, and that refers to the multiple of 8, okay, multiple of 180s, okay, it must be in the form of odd multiple of 180s, okay. So what it may looks like is that now we don't know, okay, we want to test this point, okay, this is our test point, okay, we already draw this one, and we randomly put a point over there, okay. We want to test whether this is a pools for this so-called closed loop or not, right? So what we do, we draw the line, okay, connecting the zeros to your test point, okay, and that would form the angles, okay. So we call that as angles of zeros, okay. So this may give you some values of 56, 71, okay. Then yeah, you can use trigonometric relations to find out the angles lah, right? Okay, or you can just use the Excel or MATLAB to calculate. Okay, then again form a straight line, okay, to your test point. This point we don't know whether it's a root or not, okay, and form that as the angle of pools, okay, because it's connect to the pools itself, okay. So we have θ3, θ4. So sometimes you may have more than that, okay, when your system is bracket. So you have more than that, right? It becomes more complex. Therefore, these ideas would be a simple ideas to test the locations, right? So once you have the angle θ3, θ4, okay, so this basically is 90 degree, okay, minus 180, 108, right? So why minus? Because we say angle of zeros minus, okay, so whatever you have θ3, θ4, and so on that connect to the pools itself, we minus lah, right? So minus, okay, so eventually we get this, okay. So is this a multiple of 180s? No, right? It's only minus 70, it's not 180. Okay, therefore we know that this point is not a closed loop pools. Okay, a quick test on it. Okay, why we would do this testing and so on, okay, is because when we start to design, okay, when we start our design, we may want to locate our point ourselves, okay, instead of maybe drawing the root locus beforehand, okay, you may say, okay, let's try this point, okay, it looks nice, okay, because it's just above the -3, or in this case we try such that this is just above -2, okay, we may want some value, okay, a characteristic that meet our time response specifications, okay, we try to put it there, but then it is not the root of the closed loop transfer function, therefore we reject it later on, okay. So this is how the test point will benefits you, okay. So you may try with this, okay, this value, which coincidentally will give you 180 degrees, and it is our roots lah, okay. So this is how we can use the property of the closed loop, closed loop transfer functions, okay, the property of the root locus, root locus, okay, to identify a test point, okay. So for the pools that satisfy the angle criteria, okay, so meaning to say if you get this value satisfy the -180 degree criteria, therefore now the k value we can obtain it graphically, okay. So how we can obtain it graphically is that the gain can be calculated by dividing the product of the pool length by the product of 0. Product means multiplications, all right. So this is the formula, okay, 1 over GH, which is equals to 1 over M, and coincidentally is the pool length product, okay. This sign, not a summation sign, this is a product sign, okay, symbol, okay. So again, we test with the test values, okay, just now, okay. This would be the so-called pool length, this would be the zero length, okay. So we just measure this line, the length of it lah, okay. Use rulers or whatever it is, okay, suitable for you to measure the length of it, okay. Therefore you have this equals to L1 multiplied by L2, okay, divided by L3 multiplied by L4, right? So that will give you the K value, okay, the K value of this. Okay? If this satisfy the angle criteria, okay. So if it is satisfied, then yeah, you can find the K, okay. Otherwise, this K value doesn't mean anything to you, okay, because it will not form in that particular so-called position of the roots, okay, that give you the characteristics, okay, that you desire, right? So you can always try with this, okay, so that you can see the difference, right? So that is the quick way to check, right? So we have covered from what is root locus, how to interpret it, okay, and then how to test, okay, random point, okay, whether it is a root locus or not, and how to, if it is a root locus, how we can get the gain, okay, what is the K value, okay, instead of relying on the computer lah, right? So that is the conventional way of when computer is not something very common, okay. When computer is not something very common, all this technique has been developed, okay, to quickly check, right? So now all this technique can be so-called obsolete lah, okay, but then it still serves as an important tools to check your simulations, okay, because nowadays computer is very common, but problem is that whatever it generated is still based on our input, okay. So whatever you put in, it just gives you something. Okay, is this correct or not? No one knows. Okay, maybe the program have bugs, whatever it is. So all these conventional techniques still uh, useful to just double check whether your generated solutions from the software is correct or not, right? Just a random, you just random pick few points to check it, right? So that is how engineers would work. Okay, so engineers know how to calculate. That is the basic of engineers. And then when you start to like become the team leaders or maybe the professional engineers, right? So you have to equip yourself with tools to check, okay, what others people work is correct, right? The software is correct or not, right? So this is something that uh, maybe non-engineers may not able to do, okay? Meaning to say you may come from polytechnic background, okay, as a technicians, they may able to read, okay, but they may not have the knowledge to check whether it's correct or not, okay. you can you can teach them how to plot all the graph, okay, but they don't have the knowledge to check, okay. So this is the knowledge where you use the test method to check all these things, okay, whether it's correct or not, the software is correct or not, right? So how to sketch the basic idea would be just use five rules, okay, or five major points, right, to describe a whole root locus. Okay, first would be the number of branches. Second is whether it's symmetric or not. Third would be real axis segment, and the start and the ending point, and finally whether it will go to infinity or not, right? So these five characteristics of the root locus we may want to highlight in our sketches. Okay, so the first one would be the number of branches. Okay, so again it based on certain rules itself. Okay, so this number of branches basically depends on the number of closed loop pools. Okay, so you can see that closed loop pools meaning to say you refer to the pools which consists of the forward transfer function as well as the feedback transfer functions. Okay, so based on this one, you check how many pools you have. Okay, as our mathematic knowledge says that the number of roots, yeah, the number of solutions, okay, for this polynomial, since this is highest order is 2, then you have only 2 solutions of it. Okay, therefore we know there are 2 branches. Okay, 2 branches means two line lah, because you have 2 roots, right? Okay, so if you have power of 3, power of 5, then you have multiple starting point, okay, and multiple branches, we call that, right? So it depends on the number of closed loop pools. Okay, first thing, right? Then second one would be symmetry. Okay, so how we would know that there is a symmetrical characteristic or lines occurs, okay, is that the complex closed loop pool with conjugate pairs. Okay, we always have a conjugate pairs, right? Okay, when this is a so-called second order. Okay, so we always have plus minus plus minus. So therefore, the root locus basically is always symmetrical. Okay, they always have a conjugate pair of it. Okay, and from there we know that the root locus is symmetrical about the real axis. Okay, so this is the line of symmetry. Okay, so always remember this. Okay, so we always have a symmetry line as our the real axis as our symmetry line. Okay, third characteristics when we plot it out would be the odd numbers of real axis. Okay, the finite open loop pools and the zeros will play a role lah over here. So this is the open loop transfer functions. You can see that we have +3, +4, and so on, right? So what you can do here is that you just reuse lah the same definitions. Okay, we plot the zero and poles. Okay, then we start to calculate the angles. Okay, so these angles give us 0. Okay, so this angle give us 0 because we just take the initial point. Okay, our test point over here, right? Just take random point to test. Okay, along the real axis. Okay, we only consider the real axis segment easier. Okay, so you just random put the test point over here, test point over here, test point over here, test point over here, and test point over here. Okay, you just try it on your own at home lah, right? So that you can see. Okay, so immediately you know that this line, the values equals to 0, right? Okay, this value also 0, this value also 0, this value also 0. So eventually our calculation would be equals to 0, right? Okay, very direct test locations. Okay, when we shift the locations over here, okay, we shift the test point over here, then immediately you realize that this is 0, this point is also 0, this line is also 0. But then let me change a little bit of color first so that you can see the difference. Okay, then this line, okay, this line, the purple color Mentega line, this line is no longer 0, right? So this line is 180 degree. So you have 0 plus 0 minus 0 minus 180 degree, right? So meaning to say this is, what is this? This is a roots. Okay, this is one of the pool itself, right? So immediately you know that no pools will locate on this side. No pools will locate on this side. But on this point, okay, any point along this line, the pools will locate over here. Okay, pools will locate over here. Okay, then you test over here, you will realize no pool will exist over here, but pools will exist over here. Okay, eventually you can immediately draw or realize that in this diagram, okay, in this so-called diagram itself, okay, roots will only lies on this two segment. Okay, so this is how you get used to the knowledge of it. Okay, then next would be the start and the end point. Okay, so again we have to refer back to the so-called closed loop form. Okay, the start and the end point itself, how we know where it start and where it's end. Okay, the concept of root locus will say that, okay, the root locus begin at a finite and infinite pools. Okay, so start from pools and end at 0. Okay, start from pools, end at 0, right? So previously we already draw pools and zeros, right? So therefore, from this so-called concept itself, we know that it will start from pools, end at 0. So the line would be going in this particular way. Okay, this is how we can estimate where it will goes. Okay, so the derivations you can check it out later on. Okay, so the next one would be the behavior at infinity, right? So what we realize is that I think this one is different, this different transfer function. Yeah, okay, so this one is different. Okay, so let's say now the behavior at infinity, what would occur is that the root locus, when it approach straight line, okay, approach straight line, okay, what happened would be there is an asymptote. okay, asymptote such that the locus approach infinity, going to a point where it will continues to grow lah, right? So it depends on where it, it starts and so on, right? So here what you can see is that we have three poles, okay? So three poles, any zeros over here? We don't see any zeros, right? But based on the previous concept, we say it start from poles, go to the zero, right? So no zero visible here. Okay, so what happened is that uh, from the segment concept, okay, real axis segment concept, we will see that from the pool first and the second one, the the pools will exist in between that segment, right? Okay, and alternately. So look at that particular concept without solving it. So we can see that in between the first two pools, the roots will lies along this line. So therefore, we know that these 2 points will have root locus and they will move together to meet, okay, at the point, and then they will start to separate. Okay, so this is the idea of having the concept of others characteristic, like, right? Okay, then it in between these two, no more, right? Okay, and then on the next one, again the third one, we don't know where it goes, so it will just go to the infinity line, right? So eventually we would see that there is three pools, and they will go into like uh, locations, okay, or directions, sorry, a direction such that they are equals, okay? So they are equals in terms of three lines, okay, separately. So eventually, like, they form a circle which have equal angles, okay? So this probably 120, and this one 120, right? So called roughly is like that, okay? So we can roughly sketch, okay, based on these five ideas, okay? So we can roughly sketch given a transfer functions. Okay? So next would be the root locus using computers. Okay, so this is how we can use it. Okay, you can use MATLAB with a function called rlocus. Okay, you type rlocus or maybe help rlocus, they will tell you how to use it. Or in Scilab, they call it events. Okay, events. Okay, so try it. Okay, or maybe some others online simulators, you just search root locus simulations, okay, online. Okay, then you may found some online tools, right? So here you can see that I try it using Scilabs. Okay, the code is here. Okay, you can try to type this code on your own, right? So this code referring to, I think, these situations. Okay? And then I also try with these situations and these situations. So you can see these situations occurs. Okay, the third one lah. Okay, so this one would be the first one. Okay, we say that they go here again, then go up. Okay, this one go down, right? So sometimes you will see that they form a circle, right? This one in between two poles, okay, they will go and meet, okay, then they split. Okay, so you can see that there is an asymptote. Okay, so this will form a line. Okay, same thing over here, it will go, okay, to form this so-called asymptotes, right? Asymptotes. So you can see that roughly you can sketch lah, right? Rough ideas, okay, and from there you can compare with computers. Maybe after you look at it, you feel the generated solution is a bit strange. Then you may realize that you may mistype a power over there or missing an S. So this is how you can check, okay, the computer, because computer you dump anything, it just give you the output, okay, unless syntax error, okay, otherwise it will give you a results, okay. So you can see that how it will looks like on all these things, okay. So you can try out with all the codes over here and play around with changing the values, right? So this would be useful for you for your assignments later on. All right, so here is an examples on how we can quickly sketch the root locus, okay. So we will cover this later on lah, okay, in next week lecture, so that when we start fresh with an example next week, sorry, next week is study week, so we will see you 2 weeks later, right? So this will give you a refresh on what happens, and then how you can proceed further on it, right? So this represent the end of today's lecture, okay. But before I end this one, any questions so far? Any questions?
No, doctor.
No. Okay, great. Okay. So also just to prepare you with your assignments, okay, since you already start to look into the root lockers, okay, so why don't you play around, okay, you play with the code that's given just now, okay, and start to adopt it to your assignment, right? So you just have to draw the root locus, okay, plot it out, okay, and from there you may, yeah, we may see the stability later on, okay, after 2 weeks later, okay. But this is how your assignment will slowly progress, right? So give it a try, okay. And that's all from me today. So make sure you join the sharing sessions tomorrow, right, and take the attendance. Okay, so stay safe, everyone. Thank you.
Thank you, doctor.
All right, bye bye.